Okay, what we want to do, Chapter 8, Layer 2 switching, talk a little bit about switching and the things that we can do in our network to make the network work better through the switches, because when we think about networks, or at least when I think about networks, I don't think about hundreds of switches. I think about 2 switches, 3 switches, a relatively small network. If you daisy chain switches together, for instance, what happens if one of them fails in the interim? And we'll look at some of this. We'll demonstrate some of it here in a few minutes. But you can make the half of the network go down by just losing power, losing the connection, losing a port, something like that. One of the things that we would like to have is some redundancy. Redundancy in switches, and that's really what a lot of this chapter is about, Layer 2 switching, configuring Layer 2 switching, creating switch redundancy so that if something goes down, we're not dead in the water. I probably have told you this story before, but we used to have a guy that was a really good Cisco guy that worked here, taught for a while, and then he got working back with Cisco, that had set up a network in Chicago in a large institution, and it left it up and running. And then several months later, they called him with a crisis. Their whole network went down. So they called him. He came back to Chicago, or actually slowed down, came back to Chicago, walked into the NOC, and moved one wire and collected his fee. Because they had decided to not use the protocol that we're going to talk about today, spanning tree protocol, which will allow to have multiple physical addresses and one logical, one electrical address. What somebody had done was move one of the wires, physical connectivity, and created a loop. And we demonstrated in the networking, and you can do that again, that at Layer 2, there's no way to stop a loop. How do you stop a loop at Layer 2? If you create a loop, how do you stop a loop at Layer 2? At Layer 3, we have the hop count that we can do. As we go through routers, we decrease it by 1 for every router. So eventually, we're going to time out. We're going to get to a 0, and at 0, we throw the packet away. There's nothing to do that in switches, so we have to do those kinds of configurations a little bit differently. CCN is chapter, what is Layer 2 switching, what we're going to do with Layer 2 switching. Layer 2 switching, and we've talked about this before. What does a Layer 2 switch do for you, really? Okay, it's your turn. What does Layer 2 switching, what does a switch do? Reroutes. Reroutes, not exactly. What does a switch do? We're Layer 2. What does a switch do? What does a switch create?
Packets. Well, it doesn't create packets, but it forwards packets.
Forward packets. What does it create? Huh? Collision domain. Carrier domain, collision domains, all starts with a C, right? Creates collision domains. Why is that important? Why are collision domains important? What happens if you get a collision in a network? Stops it and waits and says, okay, send it again.
Okay,
what if we can't have collisions, huh?
It's like, okay, we ran into a problem.
Okay, we ran into a problem. What happens if I have a collision out here on the interstate?
Oh, the whole interstate. Yeah.
Pile up? What happens? You think the same thing's going to happen in the network? And as we put more computers into a single collision domain, what are you going to have? More collisions. Just like if you rush hour, when do most of the collisions happen? Rush hour, because there are more cars out there. Same thing happens here. So the switches are going to create collision domains at Layer 2. And remember, we are at Layer 2. We'll talk about switching services. The switching services we're going to mostly focus on our spanning tree protocol, which is an older protocol, and then they upgraded it to one called RapidSpanningTree. I want to do a demo to show you what the differences are there and what they actually do for you. Bridges versus LAN switching. Bridges, and a lot of times a switch is called a multi-port. Switch is called a multi-port bridge. Bridges bridge in software. switches switch in hardware, which is going to make them faster. Anytime that you can find something to work in hardware, it's going to do better. Same thing when we get to layer 3, although layer 3 switches is not a topic of CCNA. You need to know that, yep, they're there, yep, they exist, yep, they do exactly the same thing that a router does, except they forward in hardware instead of in software. So a bridge and a switch do the same thing. A switch, you normally got more ports than a bridge. A bridge typically going to have 2 ports, which breaks up collision domains. Switches break up collision domains. Each port on a switch is its own collision domain. So if we plug a switch into a single device, can we have collisions? If we plug it in and we have a full duplex, we can't have collisions. That was the theory of interstates. We wanted to separate the traffic so you wouldn't have collisions, wouldn't have head-on collisions. I know people have figured out how to get across the median, but they haven't figured out how to get across the median in full duplex Ethernet. So we eliminate those. 3 switch functions. The switch functions are learning, addressing, and blocking ports. Listen, learning, forwarding, or blocking, depending on what we're going to do once we create this topology, are going to be the functions of the switches. The MAC table is something that's kind of handy to know, and the MAC table is what's going to allow us to have some security. In this room, we've configured the Cisco switch such that if James there decided instead of get on with his wireless, which he did, that he was going to plug in the wire from his computer into his laptop, it shut down the port. That's one of the things we want to look at in this chapter also. It's called port security, so that you can make your network a little more secure at layer 2. Anything that we can take care of at layer 2, we don't have to worry about at layer 3, 4, 5, 6, and 7. So if we can keep James off of our network at layer 2, then we don't have to worry about his virus at layer 7. Or we don't have to worry about him doing a man-in-the-middle capture to where he emulates something, or we don't have to worry about IP spoofing, those kinds of things. So anything that we can eliminate at the lower layers, we don't have to worry about on up. Of course, we could eliminate it at layer 1 by cutting but it wouldn't do us any good. We could cut the wire that goes to his computer, but then his computer wouldn't work, and his laptop wouldn't work either. But we don't really want to do that. Switching loops in the spanning tree protocol, and that's a big part of what this one is about. If we plug in a switch that doesn't have spanning tree, and I took a course one time, talked about, hey, if you're, on a board, you're all techs, techies, and you're bored on a Friday night, you want to see something interesting, turn the lights out, go get yourself a couple of generic switches, and create a loop and watch the light show. Create a loop. Eventually, a Windows machine is going to send a broadcast, you know that. And where does a broadcast go? So we'll do the whole lecture, and then we'll go through the rest of the topics. It goes out every port except the one it came in on. So we have 2 switches connected together, and we send it out every port except the one it came in on. It goes to the other switch. Where does it send it out? Every port except the one it came in on. Then it goes to the other switch. What does it do? Same thing. It just keeps going around and around. That's when we talk about loops, because there's no mechanism to stop the loops in a switch. Purpose of switching, and instead we've done already a lot of this, breaks up collision domains, cost-effective, resilient internetwork. They are cost-effective. A lot of what you see and read, they talk about hubs and replacing hubs with switches. Switches used to be pretty expensive. They've become relatively inexpensive based on a lot of the other stuff. Switches are really not that expensive anymore. A switch is probably cost-effective, the one device you can put in that doesn't cost a whole lot of money, that's going to improve your network substantially.
Don't get a Cisco router or switch then.
Cisco switches are not that expensive.
I've seen a couple that are.
A couple of them are, sure. If you're going to go up to a 6500, one is going to be able to take your whole topology, huge switches, but smaller switches are not that expensive. And if you go to that level with the other manufacturers, you're going to find that they're pretty expensive too. You get what you pay for. The advantage of Cisco is they just work. That's not always going to be the case. if you start with Cisco, the Cisco protocols work with Cisco devices. They don't work with other devices. There are standards. Cisco typically tends to be, if you go back and look at history, on the leading edge of the development of these things. A lot of stuff, SpanningTree, they were the first with SpanningTree. Then they improved it with RapidSpanningTree. There are standards now that allows that to work together with other switches, but that's not always going to be the case. The purpose of the SpanningTree protocol is stops loops in Layer 2 switch networks. What this allows us to do is to have a physical loop, but not an electrical loop. What it will do is to turn off one of the ports so that we don't have the transmission of data. It'll still talk to the other ports. The switches will talk about what's going on, and then if the other path goes down, it'll go through the process to bring up our alternate path, and we'll do a little demo on that here in a couple of minutes. Before Layer 2 switching, this is back to hubs. How many collision domains are here? How many collision domains on a hub? This is kind of a tricky picture, I guess, isn't it? How many collision domains do you see? I see 1, 2, 3, 4, 5, 6, because this goes into a router. A router creates a broadcast domain as well as a collision domain. The way this is drawn, there would be 6 of these things. Over here, how many collision domains? And this is still a hub. We've got the 2 servers. The server farm over here is on a hub. The hub is the ones, the Cisco devices with the arrow pointed in both directions. How many collision domains here with our server farm? 1. The servers are on a single collision domain. Could that cause us some issues? Could. Will it necessarily? Yeah, depends on how much traffic goes on. If we get a lot of traffic, just back to the traffic on the highway. The more traffic you get, typically the more collisions you have. Some of them, obviously, in traffic are more severe than others, but in these things, you have a collision, packet collision, you do the random back off and say, okay, send it again. And the more traffic you get, the more devices you put in a collision domain, the more collisions you have. So that at some point, you kind of get like in an unusable type of domain. Switch networks in here, instead of using the router to create the collision domains and the broadcast domains, we are using the switch. So instead of using a router, more expensive device, a little bit more difficult to configure than the switch, because to create collision domains in a switch, all we got to do is plug it in. We've created the same 6 collision domains here with the hubs, and we still left our server farm in a single collision domain, but we're using switches instead of the routers in order to do that, and then we just use a single connection to the router from the switch. Nothing really dramatic about that. Typical switch design in this one, lots of different connections here, but let's say that down here on these 2 lower switches, what if we had a problem with the single connection between the 2 switches down here that are going to the router? What's going to happen to the left half of our network? It's not going anywhere. So if we went into here and we made this network go away, this one go away, this half of the network is no longer going to be effective. What if we could have 2 connections between these things and the one went down? The other one automatically picks up and we're able to continue without doing anything. And that's what you would think would happen in a brokerage firm. The story I told you to start this with is why didn't they have that? Why didn't they have that protocol running on their network? So if somebody did that, they said, oh, I got a loop. Let me block the loop and find another path. Because SpanningTree is a broadcast protocol, and They didn't want to have the broadcast traffic. There's risks and rewards for everything. This is not all, there are a lot of packets. There's not a lot of data in the packets. They're very, very small packets, lots of broadcast traffic in them, and we can look at that because these things are running spanning tree. We'll look at that here at the end, if you'll let me not forget. Look at that with a Wireshark, what goes on. We can see the spanning tree from the switches that we have in here because it's a broadcast protocol. One link to the server here, again, same thing. If we have multiple switches, we could have multiple links to the server. At some point, you're kind of going to have one link to the server anyway unless you got two NICs in it, because the link to the server is typically going to be a single wire. This one, redundant topology, and as you can see, it came from a different presentation, some of the things. Redundant topology. We've created a loop here, haven't we? And the way these switches are connected, there is a loop. Is that going to be a problem? This is back to the broadcast. What happens if this server sends a broadcast message? Where's it going to go? Going to go in this segment, going to go to this switch, and both switches are going to send it where? Out all the ports except the port it came in on. So we're going to go from segment 1, segment 2, back, and then when it gets to the other switch, where's the switch going to send the broadcast? Same place, out all of the ports except the port it came in on. So it goes from segment 2 to segment 1. Got a broadcast, where's it going to send it? Segment 2. Comes back. Where's it going to send it? Segment 1. So it goes on and on and on and on and on. And we don't have a time to live like we would have in a router at layer 2. How does a router prevent that? It's got time to live. After it goes across so many routers, it says, nope, can't do it anymore. And you get back if you don't have ICMP blocked, you get back an ICMP message that says something like packet expired en route. That's typically going to be the one. If you get that one, that's typically going to be the one that said, hey, I got a loop out there somewhere, a routing loop somewhere. A switch loop has no way to stop that. How can we stop the loop? Well, if we unplug one of the wires, would that stop the loop? Yeah, but then what happens if something goes down? Now we got to go plug the loop back in. What we would like to happen is for this to happen automatically, and that's what the spanning tree protocol does for us. This is, I've jumbled these around a little bit. Layer 2 switching provides hardware-based bridging ASIC, and this is integrated circuits, which means that we're running in hardware instead of software. And again, anytime you can run anything in hardware instead of software, and you'll see ASICs, they talk about an ASIC's firewall. What does that mean? It means it's not running in software, it's running in hardware. We talk about ASICs in a router. What does that mean? It means that we're routing, forwarding in hardware and not in software. That's what a layer 3 switch is. Layer 3 switch is a router, kind of. I don't like to call it a router. It does the packet forwarding based on IP address. A layer 2 switch does packet forwarding based on hardware address. Break up the collision domains correctly, layer 2 switches. Make sure that the users spend 80% of their time on the local segment. When you and that's what this is about, is when you break these things up into segments, routable segments, what we want on the switched area is that the users spend 80% of their time within the switched area, which means that if you're spending 80% of your time going to a server, that server should be in the switched network. If you spend 20% of your time going to get information from other places, that's the ideal. That's not always going to happen. But when you start organizing these things, 80% of your traffic should be inside here in this. And if you go back to the things that we talked about earlier on, the Cisco model, we had the core, distribution, and access layer. What we want is 80% of it in the access layer. Switches don't break up broadcast domains by default. Layer 2 switches don't break up broadcast domains by, I won't say by any, because we're going to do that on Wednesday when we create VLANs. VLANs will break up broadcast domains, virtual local area networks. instead of having physical networks, we're going to have virtual networks. Same thing. And what you really do on that is like you take a switch and cut it in half and then plug a bunch of them up here and a bunch of them up here and brought them into a router. We're still going to have a router in order to make these things talk to each other. Bridging versus LAN switching. Bridges are software-based. A switch can be viewed as a multi-port bridge. We said those things. But keeping in mind that the big difference between a bridge and a switch is a switch switches in hardware, a bridge bridges in software. Bridges can only have one spanning tree instance per bridge, while switches can have many. Per VLAN spanning tree is what that is talking about, which means that if we have all these switches, and we'll go back, we'll have a picture here in a minute well, whether we get to the picture, we'll talk about the spanning tree protocol on each of the VLANs. Have a higher number of ports and bridges. Both bridges and switches forward layer 2 broadcasts. They also forward layer 3 broadcasts. They forward broadcast out all of the ports except the one that it came in on. Learn MAC addresses by examining the source of which the frame was received. So when you go into a switch from your machine, that's when it learns your MAC address. And it keeps a table of MAC addresses, and the way you see that is show MAC address table in the switch, and you can see which MACs are on which of the ports so that we can manage things that way. Both bridges and switches make forwarding decisions based on layer 2 addresses. One of the things that makes it much more efficient is that MAC address table. Once we get the MAC address that we're going to using the ARP protocol, it doesn't have to search for where that MAC address is. It may the first time. If it's not in the table, then it floods it out all the ports except the port it came in on until the answer comes back and says, oh, okay, I know where that MAC address is now. It builds its own table automatically, and that's one of the things, transparent switching, because we don't really see any of the things that are going there. The functions, address learning, forward and filter decisions, and loop avoidance, those are what we want to do with switches. Address learning, MAC address learning, so that it can send the information directly to the device that we're trying to get information from or send information to. Forward filter decisions, after we learn the address, which port are we going to send it out of? And send it out of all of the ports, and that's what a hub does, isn't it? It sends it out all the ports, and since we're all in one big area on a hub, that's the way we get the collisions. If we only send it out a specific port, then those two devices have a dedicated layer 2 connection, and we don't have the collisions. The loop avoidance, so that we can have physical loops without having logical loops or electrical loops. The MAC forward and filter table, again, would have each of these ports would be listed in the table with the MAC address. We'll look at those here in a couple of minutes. We'll put some things on and get the MAC address, show you what the MAC address table looks like. Look at some port security and look at how to make this little device here, the switch, automatically detect the MAC address so that when James tries to plug in his laptop, it says no. I mean, it'd be a real pain, even in a network this size, 150, 200 machines, if you had to go around to every switch and figure out what the MAC address was on every port and type it in. Wow. There's a command that says, hey, learn the MAC address, and what it learns is the first MAC address that gets plugged into the port. So we can tell it to do that. We can tell it how many MAC addresses are allowed on the network. This machine next to Cole here has a virtual computer running on it that sometimes I use in the security classes. Well, golly, what happens when I turn on that virtual machine if I'm only allowed one MAC address on this port? And the second MAC address comes up. Virtual machines have their own MAC address because they've got to get the information. Then it's going to say, thank you, but no thank you. It'll turn the port off. It's a great way to figure out if people are plugging in things that they shouldn't, because they're going to tell you if they can't get to the internet. don't you think? You're going to know. You're going to know when something like this happens because they're not going to be able to get out of, be able to get off of their computer. It is a way to provide a form of security at a low level. The MAC filter table, and what this is showing as these things go through E0, step 1, host A sends traffic out Ethernet 0. When you send the traffic out, the switch detects the MAC address and puts it into its MAC table. It doesn't know where anything is to start with. It builds its own MAC table. Does that for us automatically. This is the broadcast we're talking about. The nice little go around and around and around, and that's all that the broadcast does. Broadcast, no way to control the broadcast at Layer 2 unless we are able to turn off one of the ports. If we're able to turn off one of the ports, then we stop the broadcast because we stop the loop. And that's what the spanning tree protocol does for us. And this is one of those, this is a pretty simple one. 2 connections. If we had a broadcast, it would go from the left router to the right, or left switch to the right switch, and then the broadcast would come back. Automatically, FA012 is blocked. And a couple of things, spanning tree protocol. Spanning tree, bridge BPDUs, and the reason they don't want to do it, they're sent every 2 seconds. But spanning tree is set up to fail. Spanning tree, and put in the back of your head, spanning tree uses the lowest everything. Spanning tree is going to create what's called a root bridge. A root bridge is the one that all of the switches go to in order to go anyplace else. Well, it uses the lowest MAC address. It has a priority, 32,768 is the default, but all of them have the same priority. It'll get to me in a second. Same priority to start with, so we're using the lowest MAC address. The lowest MAC address is going to be the oldest switch in your network because they just keep going up and incrementing up in assigning the MAC addresses. So by default, it's going to pick the most uncapable, the least capable switch in the network to be the most important switch in the network. And that's one of the things we have to learn how to manage. And this one, you notice that on the ones, the X is on the FA012. We have a FA011 and FA012. Picks the lowest MAC address. If we have everything being equal, picks the lowest port address in order to send the information out of. So when you think of spanning tree, picks the lowest switch here. This is going to be priority 16,384, and this one has had the priority reset. It's a pretty simple command that we'll see here in just a second and use it on how to change the priority so that you can tell the system which one you want to be the root bridge. 32,768, so switch A is going to be the root bridge because the priority is the lowest. And again, lowest, think lowest in these things. Low priority. Usually high priority is good, right? Pri 1, Pri 10, Pri 100. And this one, priority high is not good. Priority low is good. So this is going to be what we're going to call the root bridge. If we had more than one, everything would create a path to the root bridge. So it can be important that you be able to configure this thing so that you dictate the root bridge, and we'll do that with the priority command, the spanning tree priority command. And they only go into increments of 4096. It's not like you can set a priority of 1 or a priority of 10, 4096 and increments on up of those. This is more of the switch loop problems that we've talked about, and again, what we want to do with spanning tree is to do that. Spanning tree protocol solves the switching loops. We have a root port, designated port, port cost, designated port. I want to look at those things when we go through. The root port is the port from a switch that goes to the root bridge. It's going to be a root port. And we'll be able to look at the ShowSpanningTree and be able to see which are our root ports. A designated port is at the other end that connects to the root port. So on the root bridge, all of the ports are going to be designated ports because the other switches have root ports to go to the root bridge, and so the root bridge is going to have designated ports to accept the connection from the root ports. Port cost is based on the speed, and they have different speed calculations depending on which iOS you have, because when we got into gigabit, they had to change a lot of the cost because they had used the lower cost of one, for instance, for 100 megabits. So what we do is look at what the cost is around the network for it to determine the best path to get there. A non-designated port is one that is actually going to be not used in it. A forwarding port is one that's turned on that's actually forwarding data. And a block port, the system is going to block the port that it determines is the one that we don't need, the one that we need to block and we don't need to forward traffic in order to stop the loop. BPDU, Bridge Protocol Data Units, are the way these things communicate, the way the system determines how we're going to get there. A non-root bridge is everything except the root bridge. We have one root bridge, and all the other ones will be non-root bridges. Another one of those, one root bridge per network, one root bridge per one root port per non-root bridge. In this one, I know it's a little out of focus, we have a 100 base and a 10 base. The 100 base is going to have a lower cost because it's faster. So let's say that the 100 base had a cost of 10 and the 10 base had a cost of 100, for instance. We're going to take the lower cost path. So it's going to take the 100 base T path from switch X to Y and Y to X. When we go on these things, the non-designated port, we have the non-root bridge has got a designated port, or excuse me, a root port that goes to the designated port on the root bridge. It doesn't show us the specifics here, but I've got a little step-by-step here shows you how the root bridge gets elected that we'll go through here in just a second so you can see the election process. The other port, or all the ports on the root bridge, are designated ports. The non-designated port here is the block port. If the forwarding port went down, it would go through the system would go through its every 2-second BPDU broadcast and say, I've got a problem. I'm not communicating on that path anymore. I need to unblock this port. It's got to go through the whole process, which can take up to 50 seconds in order to do that. That's a long time in a network. Can you imagine having let's say having your business, your online business that's selling lots of things, Amazon, down for 50 seconds? Even in a network here, 50 seconds. How many complaints in here, if it went down for a minute, do you think you would get that they can't get to the internet? Plenty. Can't get to Facebook. Can't get to Facebook anyway. Can't get to the internet. 50 seconds is a long time, and that's what SpanningTree takes. They have developed an upgrade to it called RapidSpanningTree, which is not the default protocol on the switches that you have to turn on that makes it much, much quicker, and that's one of the other demos that I want to do. And I'm saying this because I want you guys to remind me to do these demos when we get through here. So we have designated ports. The port cost is based upon the speed of the port. Designated ports are the ones that connect to, or root ports connect to designated ports. What would happen here if the root port went down, we have a non-designated here, this other one's a designated, it would become the root port because it would then go to the root bridge. And again, I'm sorry?
Would it then follow the 10 base?
We'll follow the 10 base, yes. By default, the least competent switch is the one that's going to be elected. That's why we need to know how to change the priorities of these things. If they're all the same, it doesn't really matter, but you may want to pick where in your network your root bridge goes. Spanning tree. In this one, which one is the root bridge? Priority 8192, priority 4096, priority 32768. Which one's going to be the root bridge? C, because it's got the lowest priority. If we didn't have the priorities, or if the priorities were all the same, the 32768, which is the default. And when you see these things, the first one you're going to see on the VLAN 1 is going to be 32769. It actually is 32768 plus whatever the VLAN number is. But all of them on that same VLAN have the same priority. So they're all going to be the same. They'll be a little bit different, but they're going to be the same. Designated, non-designated ports, we will look at those things. This is the speed. The 10 gigabit is 1. The gigabit is 1. This is the original, the old cost, the new cost. The 10 gigabit and the new cost is 2. Gigabits 4, 100 meg 19, 10 meg 100. As you can see, the 10 and the 100s, the old ones, they were actually pretty easy to remember because 100 meg went at 10 and the 10 meg went at 100 because you want the lower cost. The higher speed is going to be the lower cost. What we're looking for, again, in spanning tree, everything is lower. Switching loops. The statuses of the ports: blocking, listening, forwarding, disabled. And one that they didn't put in here is listening and then learning. When they switch initially comes on, and you see this on the switches, we have this amber light and nothing's happening. It's going through the spanning tree process. It's determining if there are loops, and if there are loops, it'll determine which port to turn off. Listening, it's listening for other BPDUs to determine which one is the root bridge. One that they didn't say in here is learning. There's 15 seconds in listening, 15 seconds in learning, 30 seconds. Blocking can be up to 20 seconds. So 15 plus 15, 30 plus 20, 50 seconds. That's where I get the 50-second delay before it actually makes the changes. Once it gets through, then the learning actually starts learning the MAC addresses during the learning process. Forwarding or disabled or blocked. Forwarding ports, we're forwarding data. Listening and learning, we're forwarding, exchanging BPDUs. So it sends the BPDU traffic, but not the data until it gets into the forwarding phase. Once it gets into the forwarding phase, it actually sends the data. Disable, we can use and disable is a little bit different than a block port. A block port system does. A disable port, you go into the port and use the shutdown command, where you turn it off, administratively down. Spanning tree example, we can look at these things with non-designated port. If you look at these things, we don't have any, if we don't have any priorities in these things, we've got to assume that they're all the same, 32768 the default. Then the MAC address will determine which is the root bridge. So this one is 000. Everything starts with 00, 4 zeros, right? 000. And then we have 8C00, 8C00, 8C00 on all of them. So the last grouping is going to determine 1201, 8955. 1201 is lower than that, right? 1201 is lower than 2101. 1201 lower than 1202, but just barely. And it's lower than 9870. So we have now elected the root bridge. And again, I want to show you a little flash on how that works. Each of the devices are going to then determine the cost to the root bridge. And let's say that all of these, just for simplicity, are a cost of 10, since they didn't tell us. 10, 20, this one would be 10. We're obviously going to go there. If we went the other direction, it would be 10, 20, 30, 40. Well, 10 is a whole heck of a lot less than 40, right? We go down to this second switch, we can go 10, 20 or 10, 20, 30. So we're going to take the 20 path, the lower cost path. So each of these have root ports. The root ports go to designated ports, and the designated ports are not just on the root bridge. All the ports on the root bridge are designated. But we can have designated ports. Designated ports connect to root ports.
On the designated, the switch, that top designated switch?
This one?
Yeah, I thought that one would have the blocking on that one.
No, this is the root bridge. This is the root bridge. We're trying to get to the root bridge, right?
Yeah.
So we're trying to find the lowest cost path to the root bridge from all of the non-root bridges. That's where we're going here. So we're going to go to the 1020. The 1020, we're not going to use the 30. And then this one, 2101, why did it pick the 9870 to block? Because it's higher than 2101. Again, lower. Everything lower in spanning tree, which is kind of, I guess, goes against what we normally think about. We normally think about higher the better, but in this case, the lower the better. All lower. Problems with PCs, and this is the RapidSpanningTree. PCs can boot faster than 30 seconds, and 30 seconds is if you didn't have any blocking time, and the blocking time is a random time, up to 20 seconds. And I always use 50 because that's the worst it can be. What happens here, and what happens a lot is, and you have seen it here, I think. I changed the switch over on this side at least to turn it off with the port fast command. Really complex spanning tree port fast. What that basically does is turn spanning tree off. Says, don't do that. I don't have any switches. I can't create a loop. I only have access devices, computers on these ports. They come on instantly. If they didn't, you ever sit down at a computer, try to log on, Control-Alt-Delete, and the authenticating server is not available? I know you have. There are some things that cause that. Spanning tree is one of the things that causes that. If you don't configure the access, the true access ports to machines, using the port fast command to turn spanning tree off so that they come on instantly. Because you've got to wait till it goes through that 30 to 50 seconds of, let's see if I've created a loop, before it'll actually turn the port on and start forwarding data. So port fast does that. The other problem is, see, problems with the uplink ports, 50 seconds of downtime causes big problems. And again, we'll look at those things here in a few minutes. So what we want to do, switches are handy devices, lots of configurations that can happen on them. ShowSpanningTree, and again, not great, but if you use, not great focus, if you use the ShowSpanningTree command, VLAN 0001, tells you by VLAN which ports are which. We can have different priorities on different VLANs when we create our other VLANs next time, because we had that one link on all of these things that just wasn't used, right? What if we would decide, hey, let's make this a little more efficient, so let's have different priorities on different VLANs. We would have different block ports for different VLANs. We could use that link that's blocked for a different VLAN. Each of these things, it will tell you this bridge is root. It will tell you which is the root bridge. If it's not the root bridge, it will tell you which port goes to the root bridge. It will tell you the bridge ID of this, priority 32769. And it says here the priority is 32768 plus the system ID. The system ID is whatever VLAN number it's on. This is on VLAN 1. So we add 1 to the 32768 to get 32769 for it. If it was VLAN 10, it would be 32778. VLAN 100 would be 32868. So it is there. And then what are each of the ports here? FA01 is a designated port, and it's in a forwarding state. If it's in listening, learning, one of those other states, it'll tell you listening, learning, forwarding, or blocked. Designated, all these are designated ports, and they're forwarding. Forwarding port, we're going to, a forward port goes to, we're going to a root port for a designated port. Designated ports connect to root ports. These are the states, the listening, learning, forwarding, blocking. And from this one, he calls it the bonus. The switch will wait up to 20 seconds before moving a block port into the listening phase. Listening, 15 seconds of listening for BPDUs. The switch sends and receives BPDUs. Bridge protocol data units, BPDU. Listening, learning, 15 seconds of learning MAC addresses. It populates the CAM table, content addressable memory. First time I ever saw that, I said they spelled MAC wrong. But they didn't. It is the MAC table, but Cisco calls it content addressable memory. When you see that, think MAC, CAM MAC, all the same letters. And then we go into forwarding state. The port's forwarding traffic. It's forwarding data. Up here in learning, it's BPDUs are going back and forth. So it is actually sending information, but it's the BPDUs. Rapid spanning tree, we still have all the same things. We have the root ports, the designated ports, but instead of calling it a block port, we call it an alternate port. A little bit different than spanning tree because it actually remembers where the alternate ports are, considers it a backup port. Kind of like EIGRP remembered the other paths. This remembers that it can be a designated port. In spanning tree, once it goes down, it has to go through the whole negotiation process. Rapid spanning tree doesn't. It remembers. It keeps things in memory. Rapid spanning tree, again, is not the default on the switches. You have to turn it on, which is not real hard. It's like spanning tree, IP config, or not IP config, go to config, spanning tree, mode, rapid spanning tree protocol. So that takes care of my discussion on that. Let me go through this demo of how this would work, spanning tree demo, and it's on the Moodle page, obviously. So we're going to start this thing, bridge A, B, C, and D, and I can't make these any bigger. They each have a different MAC address, obviously, or bridge ID. And the bridge ID, the priority on each of these is 32768, so we're going to use the MAC addresses to determine the root bridge. So these things are connected. Do we have a switched loop here? Do we have a switch loop? I think so. Can you go all the way around? It's connected, so we have a loop. Not good at layer 2, right? We need this system to be able to say, I want to do something different. So each of these guys, they boot up. All the bridges think of themselves as the root bridge. So they're going to send out BPDUs that's saying, I'm the root. Assume that the first step is that bridge C sends a BPDU to bridges A and B, announcing that bridge C is the root. Root ID 32768000002 at the end. Note that the B's root ID will change from 3 to 2 because 2 is less than 3. So next we go, bridge C sends us out and says we're going to go to 2, and when we get up here to bridge A has a lower ID 1, lower than 2, or lower than 3. So he should eventually be the root. My root is higher than root C's root. C is root. That's what B is saying because it's just gotten the BPDU from C and not A. So now C and A are claiming to be the root. Soon as the next step, A sends BPDU to bridges B and C, announcing itself as the root. B and C, because its root ID is 1, they're going to now accept it as the root bridge. Since it's BPDU information, okay, I've got a 1. My root ID is higher than A's. A is root. So we have now elected, finally, the root bridge. My root ID is higher than A's ID. So all of them now agree that A is root. Once that happens, everybody must select one root port to get to the root bridge. We're going to assume that each of these are the cost of 1900 megabit per second. Which one do you think is going to block? Root port, those are pretty obvious, right? The single connection, the cost of 19. Now, which one ports providing the least are elected as the designated ports connect to the root port. It's referred to as the designated bridge, and each of these are designated bridges, 3 segments, 1, 2, and 3. Designated port, designated port. So designated port going from here. Why is it the designated port? Probably can't see that, but its ID is 2 and the other one's ID is 3. So which one's going to wind up being the blocked port, do you think? Forwarding based on priority. And which one's going to do the forwarding? Here we finally got to the block port. The one with a higher ID is going to be the block port. The lower one's the one that's going to be forwarding. It's still a designated port. It's still in forwarding state. But it's forwarding to something that just says no. It's there available for use if the other path goes down. So we've now gone through the election and sent in the BPDUs. And then what this is showing over here is the one with the block port still sending the BPDUs in case the other one goes down, so that it can change the state of the connections, the state of the network automatically. And again, advantage to this thing, if it's turned on, is each of these can automatically change state based upon the state of the network. So that if somebody comes in and creates a loop, we can prevent the loop. If something goes down, we can change the logical topology of the network automatically. Questions? Let's take a break here for a minute and we'll do a couple of demos and then we'll get into the lab. This is a typical, we're going to demo loops, what's going on, and we have a loop here. And a couple of things that we talked about. One is, how do we find the root bridge? Because this one doesn't give you any real good indications, does it? Everything's going to be 32768, that's the default. They're all connected with 100 megabits per second. Okay, good. We have a blocked port here. It's amber down here. FA02 on switch 2 is the blocked port. So which one is the root bridge? This is actually pretty easy to guess, isn't it? What do you think? The top one probably. But how can we be sure? How can we be sure? Let's start here so we can see a couple of things. ShowSpanningTree and SPA tab will get you there. Use the tab key. You don't make typos. ShowSpanningTree says that the port says the root ID priority 32769 to 32768 plus 1, VLAN 001 that we're on. Address is 00B BE 83 7D 5D. That's the MAC address of the root bridge. And port 3, fast Ethernet 00 would be the way we would go out. If we go down here a little bit farther, we find a fast Ethernet 03. Role is root, it's forwarding. So the root port goes to, where does the root port go? To the root bridge. It's the path to the root bridge. It goes to a designated port. And in this case, we don't have a whole lot of choices since we only have these very few. So that probably would be a good guess. Well, if we have more routers, or more switches, you might have to follow this path a little bit further, because its path is going to be, we're going to say the root port, that's the way it goes to the root bridge. If there are more, then we might have to keep going a little bit farther. Let's go up to the one that we think is the root bridge and see what it tells us. It should tell us that it is the root bridge. ShowSpanningTree. This bridge is root. So we have the root bridge. To show the root bridge, the MAC addresses, well, let's look at MAC addresses here in just a second. We'll do the port security. What I want to do here is, and I've got a ping going from PC1 to PC0, and it is pinging. It's working just fine. Now let's see how long it takes SpanningTree to recover if we mess it up. So let's go into this switch right here. What port was that on? Yeah, I want the one at, 3, thank you. 3, so let's go into config T, intfa 03, and do a shutdown on it. And let's go back to our computer here. And it's shut down, it's red. We're now in timed out. We're going through the negotiation process over here. Try to get this out of the way so we can see stuff. We're still amber, but it is the BPD user saying, the path is no longer effective. So how many people do you think would have complained by now that the network's down? Now we're up, we're communicating again. Let's go back in, bring this one back up. I'll switch to the other one, and now we're doing the same thing. I'm bringing it back up. We're timed out, and it's going to go through that same process. The listening, learning, so on. The block is a random one. This actually does. I don't think that the packet tracer actually takes as long as a real switch will, because it'll take 15 seconds in listening and 15 seconds in learning, plus whatever it gets from the block state. So now it's back up, ready to go. Let's go into these things, and we said that the RapidSpanningTree should work faster. SpanningTree mode. See, in Rapid, the PVST is per VLAN SpanningTree. So we're going to put this one in Rapid PVST. That's switch 0. Let's go to switch 1. Do the same thing. All of the switches have to have RapidSpanningTree protocol running on before that protocol works. If you have even one switch in 100 that has the 802.1d, and that is SpanningTree, then that's what everything will downgrade to. 802.1w is RapidSpanningTree. I guess if I went to enable, config T would work better, wouldn't it? SpanningTree mode, RapidSpanningTree. So we got it on switch 0, switch 1, so now let's go to switch 2. Mode. Now if we do a ShowSpanningTree, it says that the protocol is RSTP, RapidSpanningTree protocol. Let's go into this switch and go back to our interface and see after we get because we're still negotiating here, huh? I think it just didn't change. INT 0, 3, right? Like, first of all, let's see if we're still pinging. We got it timed out here. Okay, now then. Guess I made a mess out of it while it's figuring it out, huh? Notice over here, all this, they changed the protocol, they all went down, and now we're back up, I hope. So let's go to switch and interface and do a shutdown on it. One of the things that's happening is to avoid some of the negotiations on the computers, and one of the other things I said we'd look at is port fast. Port fast turns off spanning tree protocol. So let's go over here to these guys, and they should be on port 0. Let's go to this one and go to INT maybe. INT, fast Ethernet 0, 4, spanning tree. Actually, we have to do an access port, so we're going to say spanning tree. No, we're not even going to say switch port, mode, access. We have to put these things in access mode, and then we're going to do spanning tree port fast. And it tells you that port fast has been configured, on and on and on and on and on and on about what it will and won't do. I'm going to go ahead and go to switch 2 and do the same thing. 0, 4. Switch port mode. First we have to tell it it's an access port, and we haven't talked about the type ports. We will. In VLANs, 2 type ports are access ports and trunk ports. Access ports are the ones that go to computers. Trunk ports go to switches, switch to switch. So spanning tree port fast should turn that off. And let's test that out. Let's turn our computer off and turn it back on and see if it goes through all of the negotiations here. So we'll go to the physical, turn it off, turn it back on, and it's still going through the negotiation. I guess I got the wrong port. Huh? Now it's back on. It's up. So we're still going through negotiation of this thing. So now that we've changed that, let's go back into this thing and see what happens. I guess we should start back our ping, huh? Ping 192.168.1.2. Okay, it's pinging. So I need to do the T switch, which keeps going until we tell it to stop, the time switch. So now let's go into our switch, Internet Fast Ethernet 03, and do a shut. I don't think I even got back fast enough, did I? You can see it didn't even drop a ping with the RapidSpanningTree configured. Let's go back and do the no shut on this one, and it probably will drop maybe 1. And you can see how fast that it actually changes here. I can't get back quick enough, and it didn't drop any on this one either. Now there's our 1 dropped ping. So RapidSpanningTree does the same thing as SpanningTree does and makes it quicker. It also stores the alternate ports, the backup ports. So take a quick look at port security. Go into the command line, and let's do it on this one that the computer's on. And let's go in here and config T, INTFA 0/4, switch port. The way you turn it on is switch port security. You have to give that command before you do anything else. We're going to switch port security that says that we can do the MAC address, and then the way that we make the system determine what it is use the sticky. Otherwise, you can type in a MAC address. Sticky says that it should learn the MAC addresses for me. Switch port security, and then how many do I want? Let's say that the maximum that we want on this one is 1. And then what we're going to have for violation, the default for violation is shut down, but I always just because violation shut down the port if we get more than one MAC address on it. Show MAC address table says that we have a static MAC address. Dynamic means it's going to change. Static says that it has remembered it. And if we do the show run, right here in the run, interface fast Ethernet 04 has port security and it has a MAC address on it. I guess the way that we could actually see if this works is, let's go in here and let's put a hub up here. Now let's disconnect this machine from here. Connect the hub to 04. That's the one that had the MAC, that had it, right? And then connect my computer to the hub. And let's go in here and put a second computer in here. See if we can make this thing break. Did I break it? Port's down. Because I have 2 MAC addresses. When it got to first do anything with the second MAC address, it turned the port off. The only way to get back from here is you got to go to the port and do a shut and a no shut. Take the extra MAC address off. But port security, you can protect yourself with it. You have to turn it on, then tell it what you want it to do. So that's the port security portion of it. Questions? What was it we were going to do that we didn't do?